When you open an app, stream a movie, or send a text, the path that data takes feels completely invisible. Most of us imagine an ethereal cloud, or radio signals bouncing effortlessly off satellites suspended in orbit. But if you mapped out all international data traffic right now, you'd find that those satellites handle less than 1% of it. The reality is much more tangible. Over 99% of international data travels through thousands of miles of heavy, physical cables dragged across the bottom of the world's oceans. Every financial transaction, every video call, every email you've ever sent abroad, it all squeezes through a tube that is roughly the width of a garden hose. Our modern digital existence is anchored by a physical tether, forced to survive in the most hostile, crushing environment on Earth. Inside that hose are strands of ultra-pure glass, no thicker than a human hair. Lasers pulse data as light, and because of total internal reflection, those pulses bounce perfectly down the inside of the glass. This chart displays light signal strength over oceanic distances. Even in ultra-pure glass, light inevitably dims and scattering, but every 50 miles, an optical repeater catches the fading light and spikes it back to peak intensity. Because these repeaters are sitting out in the middle of the Atlantic or Pacific, they can't just be plugged in locally. They require a continuous feed of up to 10,000 volts of electricity, pumped directly from power stations on the shore. Moving all that data requires building and maintaining a continuous, highly charged electrical circuit across the span of an entire ocean. Once that circuit is powered, it has to survive. The ocean floor applies thousands of pounds of crushing hydrostatic pressure per square inch, while resting on active, shifting tectonic plates. To protect the glass, manufacturers build a dense fortress around it. The delicate fibers sit inside a polycarbonate tube, surrounded by an aluminum water barrier, all wrapped in tightly stranded steel wires. That aluminum layer serves a highly specific chemical purpose. It blocks hydrogen molecules and seawater from seeping inward, which would gradually turn the glass cloudy and destroy the signal. The steel wires are there for physical tension. Without them, the cable would simply snap under its own massive weight when a ship attempts to deploy it into deep water. Finally, the entire structure is coated in a thick polyethylene jacket, formulated specifically to grind against jagged seabed rocks without tearing. The vast majority of an internet cable's physical bulk is just dead weight, defensive armor built solely to protect the tiny fraction of a percent inside that actually carries the data. Getting that armor into place requires a massive industrial operation. Highly specialized maritime vessels are loaded with thousands of miles of continuous cable, coiled in massive tanks below deck. Deploying it is a delicate physical balancing act. If you lower miles of heavy steel armor into water that's thousands of feet deep, the tension risks snapping the line under its own weight. As the ship nears the shallower waters near the shore, specialized remote submersibles dive down to drag a plow through the seabed, physically burying the cable beneath the dirt to hide it from coastal threats. Expanding the global internet is a slow, heavy machinery maritime operation. Despite all the steel and polyethylene, these cables are severed between 100 and 150 times every year. The damage is highly concentrated at narrow maritime choke points, like the Red Sea, where dozens of lines are clustered together. The environment rarely breaks them. The primary threats are human, massive ship anchors and industrial fishing nets that drag across the bottom and catch the lines. When a line is cut, a specialized fleet of repair ships springs into action. They sail directly to the fault line, lower a hook to grapple the broken ends from the ocean floor, pull them up to the deck, and splice the microscopic glass back together by hand. You rarely notice when a cut happens because the system survives through redundancy. If a cable snaps off the coast of Egypt, routers instantly redirect your traffic through an alternative path around the Cape of Good Hope to keep the data moving. The internet is a fragile physical triumph, surviving only through precise engineering and constant maintenance at the bottom of the sea.